Discussion of collisions, and we're going to be talking about 2D collisions today. So I've got an example problem here we're going to be working through. Now, in the example problem, we have two cars that are going to be colliding in an intersection. One car has a velocity of 16 meters per second to the right. The other one has a velocity of 21 meters per second upwards, and they're going to hit, and this is going to be a collision in 2 dimensions. When they collide, they're going to stick together, which makes this a perfectly inelastic collision. And they're going to both move off together as a jumbled mess in a certain speed and a certain direction. So let's read the problem. So a car has a mass of 950 kilograms and a speed of 16 meters per second. It hits the truck. The 1,300 kilogram truck is traveling at 21 meters per second. They collide and stick together, like I just said. You want to find the speed and direction of the wrecked vehicles just after the collision. And we're going to make an assumption that the external forces can be ignored. So that automatically tells us that what? Momentum is conserved. And even though this is a 2-dimensional problem, the principle of conservation of momentum during a collision is going to be what we're going to use here. Alright, so to get started, let's write out what we know. We know the net momentum before the collision is equal to the net momentum after the collision. Okay, so all we have to do is use this and we can actually solve out this problem. So let's go ahead and expand this. Okay, net momentum before. Well, what that is the net mass times velocity before the collision. That's going to equal to the net mass times velocity after the collision. Oops, there's an F right there. Okay, so let's go ahead and work this out. Now there's two objects in the system before the collision. We've got the car and the truck. And the car, according to the problem, has a mass of 950 kilograms. So we just write 950 kilograms, that's the mass, times the velocity, which is going to be 16 meters per second. But remember, we're talking about more than one dimension, so we have to be careful here. The car is moving in the positive x direction. So it's going to be 16 meters per second x hat. Alright, so I'm just going to write car up here so I know what I just wrote. This is the car's momentum, plus the truck's momentum. The truck is larger, it has a mass of 1,300 kilograms. Alright, and we're going to be multiplying that by the velocity of the truck. Now remember, it's a vector, so it's going to be 21 meters per second, but not just 21 meters per second, it's 21 meters per second y hat. Okay, its velocity is in the y direction. And we'll of course set this equal to what? Well, in the final state after the collision, these two are really acting like one body. They have the same velocity, the same direction, the same position. They're crumpled together. And the mass of that crumple is going to be this. It's the mass of the car, 950, plus the mass of the truck, 1,300. And then the momentum of this is going to be the mass of that crumpled mess multiplied by its velocity vector. So I'm going to write v after the collision. So here's the car, here's the truck before the collision, and this is going to be, I'll just write car truck, since they're going to be collided together. Okay? So it's a simple vector equation. It's got one unknown, the final velocity, and that's what we're trying to figure out, right? We're trying to figure out the speed and the direction after this collision. Okay, we worked this out, just multiply these two together, and let's keep the units on these so we can see what's happening more clearly. So this times this is going to be 15,200, and the units are going to be the units of momentum, which are kilogram meters per second. Okay, this is in the x hat direction. So we multiply the 950 and the 16, and the x hat stays there. Plus 1,300 times 21. This is going to be 27,300 kilogram meters per second. in the y-hat direction. And you know what? We're done. This is a momentum before the collision. So we're going to set this equal to, okay, 950 plus 1300. This is a total mass. The total mass is going to be 2250 kilograms. So the total momentum is going to be that times, you just bring down the v after. All right. So we're trying to solve for your final velocity vector, and in an ordinary scalar equation, we would just divide both sides by 2,250. And you know what? Since this is a since this is a scalar, we can just divide by that number. It's fine. So I'm going to divide both sides by 2250 kilograms. Just like that. Okay, and what happens over here? How can we divide this, what's really a vector with two components, by one number? Well, we just divide each term by this number, okay? So we divide this term by 22,050, or 2,250. We divide this term by 2,250, and we get 6.755. And look, the units, they're going to be meters per second. So it's 6.755 meters per second in the x-hat direction, plus this divided by this, you get 12.13 meters per second in the y-hat direction. And that's equal to your final velocity. Now, if the problem was just asking you to find the final velocity, we'd be done. Look, just as we would expect, the x component and the y component are both positive. This is going in the first quadrant, in some direction in the first quadrant. We know the x component, we know the y component. This vector is totally defined. But what it's asking for is the speed and direction. So now our job is just to turn this vector into its magnitude and direction. Okay, well, first of all, magnitude of a velocity vector, that's just the speed. So we're trying to find the speed and the direction. Okay. So speed is pretty straightforward. Speed is equal to the magnitude of the velocity vector. And we know the Pythagorean theorem lets us write out this. It's going to be the square root of vx squared plus vy squared. Okay? Well, where do we find the x component and y component of velocity? It's right here. It's right here in the unit component form of our velocity vector. So it's the square root of 6.755 squared plus 12.13 squared. All right? You work that out, and you get the speed. Your speed is equal to 13.89 meters per second. And that's half the answer right there. That's how fast these two vehicles are going to be running off. Now let's go back up to the actual picture. 13.89. So now I can write in, this is 13.89 meters per second. We don't know the direction yet, but we're going to be able to find it. So look, we know when two objects collide, it's a totally inelastic collision. That means a lot of kinetic energy is being lost, and that makes a lot of sense here. Look, the car was going 16 meters per second, the truck was going 21 meters per second, and now they're both going at about 14 meters per second. So they both individually lost speed and lost kinetic energy. So overall, we've lost a lot of kinetic energy. Now, when I'm asking about the direction, what I'm really asking about is this. If you take this velocity vector, it looks like 45 degrees, but we don't really know what it is yet. And we were to draw a little dotted line like here in the positive x direction. It's the angle between the vector and that positive x direction that we're going to go for. This is the theta, or the direction of this vector. Okay? Oops, went too far. Okay. So We know it's going to be in the first quadrant since both the components are positive. So positive, positive, it puts it in quadrant 1. So let's see, direction, which is going to be our theta. We're just going to use the inverse tangent method. It's the inverse tangent of the y component divided by the x component. And the y component is going to be 12.13. The x component is going to be 6.755. That's all we have to do. All right, and that's going to be equal to. Now, you can't do this unless you have a calculator or you have a giant table of trigonometric functions. So I put this in my calculator and I get 60.89 degrees. That's my direction. It looked like 45, and in fact you might even think it was 45 just looking at the problem, but it's really closer to 60 degrees, about 61 degrees here. So we have both the speed and the direction of our velocity vector, and that's what we need to find, so we're done. All right, thank you.